Honghao Gao from Honghao University, who is going to talk to us about Legendrian knots and Lagrangian fields. So let's welcome Honghao.
All right. I want to thank the organizer for inviting me to give a talk. And since I think this is one of the last talks of the entire event, let me, on behalf of everyone in this room, to thank the organizer for making this successful congress. So the slogan of the talk for today is I'm going to explain to you the following relation between contact and sympathetic topology and some algebra. So we're going to look at Lagrangian knots inside some context 3 manifold, and on the algebraic side, we're going to have some DJ algebras and sheaf theory. And correspondingly, we have Lagrangian fillings in 4-dimensional sympathetic manifolds, and the corresponding algebraic story are cluster algebras. So let me begin with the very basics. The sympathetic manifold is an even-dimensional manifold equipped with a closed and non-degenerate form. The parallel story happening in odd-dimension is contact manifold, where the contact structure, this C here, is a non-integrable rank 2n distribution. So the non-integrability locally means the following. We can write this distribution as a kernel of a one form, and this one form alpha, which d alpha to the nth power is non-zero. So that's very similar to the non-degeneracy condition for the sympathetic form. So in the 80s, Eliashberg made great progress classifying the contact structures. He introduced the notion of over-twisted contact structure, and in contrast, the tight contact structures. And in years to follow, there has been a lot of progress in the classification of contact structures. For example, the work of Casals, Petroli, and Presses in dimension 5, and Woolman, Eliashberg, Murphy in all dimensions. For this talk, we're not going to look at all contact structures, but a very specific one as manifested here in this picture, which is the standard tight contact structure on R3. So in this particular form, this contact 1 form can be written just as ez minus y dx, which satisfy this property we want here. So what is the Lagrangian knot? First of all, a knot is a smooth embedding of a circle inside R3. If I have multiple components, a disjoint union of knots, that's called a link. But I'm not distinguishing knots and link too much in this talk. And the Lagrangian condition means that the pullback of the one form to this S1 is equals to 0. And there are certain knot diagrams we can use to plot these knots. One is the from projection, which we just send out to the xz coordinate, and the other one is the Lagrangian projection, which we send it to the xy coordinates. So here's the example of the Lagrangian unknot. As you can see, that the topological knot type of this is just a circle. But when we look at this knot in different directions, based on this coordinates, it either has its cusps or this double points appear. Some more complicated behavior compared to the smooth knots. So here's another example. This is the next simplest knot in the knot table, the right-hand trefoil. And you can see that here's a from projection. It has this cusps and crossings, and the Lagrangian projection. This is a inverse Lagrangian curve inside R2. So one question people usually ask when they first see this topic is that fix the smooth knot type, how many different Lagrangian knots we can have in there? The answer is there are a lot of them. The reason is that is this construction called stabilization. Um, what it means is that we can approximate a strand by all these zigzags. Okay? So from the previous slide, you can see that these zigzags are some allowed phenomenon we can draw in the front projection for Lagrangian knots. And if we take a front diagram of arbitrary Lagrangian knot, you can add a lot of these zigzags to any location of the strand. So presumably that creates a different Lagrangian knot. And how do we know that? We can actually argue about that very easily using some classical invariants. There are two of them which are numerical. One of them is the TB, the Thurston-Banach number, and the other one is the rotation number. So the Thurston-Banach number is a linking number, so some topological construction with respect to the red push-off, which in our coordinates is just a partial z. So we have the knot inside the R3 space, and then we just take a second copy and flow that along the z direction, and then you can compute the linking number between the two copies. That is the Thurston-Banach number. So this idea using the contact structure to define this linking number was brought up by Bill Thurston in the late 70s and written down explicitly by Daniel Banach in 83. And the other invariant is the rotation number. This is sort of the winding number of the tangent vector of the Lagrangian knot inside the contact plane. And the contact plane sort of behaves like a symplectic vector space after some trivialization. And you can look at the winding number in there. So that's some version of the mass of index. So you can use either one of these invariant and find out that the stabilization actually changes the Thurston-Banach number and the rotation number. So for any Lagrangian knot, doing this zigzag keeps the smooth knot type but changes the TB and the rotation. So those are some effective numerical invariants tells the Lagrangian knots apart. So the next question is like, using these two invariants, how far can we distinguish Lagrangian knots? The next theorem was by Eliashberg and Fraser in '98. They proved that if lambda is a Lagrangian knot whose underlying smooth knot type is the unknot, and it is Lagrangian isotopic to one of the following knot in this table. So, so this is a diagram of Lagrangian knots. All of them have a smooth knot type as the unknot. And I put them as the integer lattice on Z2, where the coordinates are the horizontal one is the rotation number, and the vertical one is the Thurston-Banach number. And you can see that all of them can be derived from the top Lagrangian unknot, which has the maximum Thurston-Banach number, and then start doing zigzags in different ways, and then sort of builds this mountain shape of Lagrangian unknots. And the theorem of Eliashberg and Fraser basically says, that's all of them. Any unknot, Lagrangian unknot is uniquely determined by these two numerical invariants. So if that's the only case we look at, we sort of feel like the Lagrangian knot theory is not much different from smooth knot theory, but that is simply not true. If we look at more general knots, the story become more complicated. There's a very interesting example. I'm not going to explain the details here, but NR and Honda studied some cable knots, and then they find some very interesting behavior of such diagram, and that's their one of their famous work, 05 in Annals paper. Okay, so that leads to the following question. Again, how much different Lagrangian knot theory is from the smooth knot theory? So let me be more precise about the statement here. So the question is like, do we have two Lagrangian knots, lambda and lambda prime, such that they are just they have the same smooth knot type and the same Sturzenbank number and the same rotation number, but these two knots are different as Lagrangian knots. In other words, if we we're able to put all Lagrangian knot in such a mountain shape, is it possible to put more than one candidate in one spot? That's called the Bodney problem. So to answer this question, what we really need is some sympathetic technique, and one of the most famous technique appeared in the past 40 years is this story of the J homomorphic curves. So this all starts in the Gromov's celebrity paper in '85, where he used the technique of J homomorphic curves for the first time in sympathetic geometry, proved some non-squeezing theorem and a bunch of other interesting results. And later in the late '80s, Furr used this this technique to build a complex, which is now called Furr homology, and use that to solve the Arnold conjecture. And at this point, it's a homology theory. And then further in '93, I think Fukaya further categorified this and make that into the Fukaya category. And you have hearing about these constructions throughout these 2 weeks. So that's now become main theme in sympathetic geometry. So on the context side, this J homomorphic curves was first Eliashberg in '98. He outlined the construction for contact invariants. Okay, so how to put that in the context setting, and later in 2000, Eliashberg, Giventhal, and Hofer set up the framework of SFT, so sympathetic field theory. So that's some version of topological field theory, conformal field theory, kind of thing, where the sympathetic, the field theory here, depending on who you are, it may refer to different contexts. But one of the the philosophy is that we should consider the cobordism as functors, and the sympathetic refers to the definition of the functor involved involves the counting of J holomorphic curves. So that's a framework. It's still ongoing inspiration until these days, and that works in like it's a general slogan in arbitrary dimension. In dimension 3, once dimension is low enough, Chekhov was the first person who made this construction rigorous. So what he did is that he take the Lagrangian knot lambda, and he is able to define, using the principle of SFT, DG algebra associated to lambda. It's a differential graded algebra. And moreover, this is an invariant in the sense that if two Lagrangians are Lagrangian isotopic to each other, and then their associated DG algebras are stable Taylor isomorphic. So that's a stronger notion of quasi-isomorphism in the category of DG algebras. Okay, so he used Chekhov very successfully used his DG algebra, distinguished these pair. This is called the Chekhov pair. Mm. So in the knot table, um, these pair of knots are called mirror of 5-2. So the smallest number of crossing for the smooth knot type has 5 crossings, and then it's the second knot in that table and taking the mirror. And this is also called the twist knot. So Chekhov find this pair of knots where they, it's a positive answer to the botany problem. These are smoothly the same knot, same Thurson-Banach number, same rotation number, but using his more powerful invariant, DG algebra, he's able to show that these two Lagrangians are actually distinct. So there's really deep sympathetic geometry behind just those two numerical invariants. So let me give you a quick glance of Chekhov's definition, so that you got a sense of why this is a SFT invariant. So the DG algebra, this is a free non-commutative algebra generated by the rep chords, which are also the double points in the Lagrangian projection of the knot, and also some formal variables associated to the fundamental class of lambda. And the grading is given by the Cauchy-Zander index, which is the relative version of the mass of index. And the differential is given by counting immersed disks in the Lagrangian projection. So let me show you this one example. This right-hand trefoil. You can see that the Lagrangian projection has all these crossings, which corresponds to the double points in the Lagrangian projection. It's an immersion. And I put a mark point, which is the dual of the fundamental class of this circle. And we have some grading, and the differential, for example, this A1, this double point, it has like the differential has like 4 terms: 1 plus B1 plus B3 plus B1 B3. If we look at this very inner region here, you see this is a immersed disk whose boundary is on lambda, and there are 4 corners which are A1, B1, B2, B3. So that defines this term monomial inside the differential of A1. And we can also seek for other disks, and that gives the 4 terms. So some version of such definitions. Okay, and I should say, like just from this definition, the SFT recipe is really here. The differential is given by counting immersed disks. But in terms of making that applicable, to distinguish knots, this algebra itself, it's a non-commutative algebra generated by the crosses. So generically, we know that there are finitely many generators. That's a good story. But having this, free algebra, which makes this really large invariant, and it's hard to make that computable in a suitable sense. So it's not computationally practical to distinguish Lagrangian knots. So Chekhov actually did something more. In the very same paper, he introduced this notion of augmentation, which is just a DG morphism from the DG algebra to this is a trivial DG algebra, and K is the field that we would like to choose. So another perspective is to think about this epsilon as a K point in the DGA, functor of K points. And then also he introduced the notion of linearized homology, LCH. It depends on lambda and it depends on the choice of this augmentation. But this is a finite dimensional gradient vector space generated by the ripcords, as a vector space. So somehow he is able to linearize this non-commutative DG algebra into a vector space, so making that a homology theory. It's the same set of generator as we had for the algebra. Like this time, it's only like the linear span of those. Okay. So once he's able to linearize the DGA, this is generically finite dimensional and it's computable, and you can just use a dimension to distinguish the Chekhov pair. That's what he did. And there are some follow-up constructions. Let me mention them. So in the paper of N.R. and Sablov, it's a follow-up paper. They realized this DGA in the simplexization. So instead of doing the Lagrangian projection to R2, they add one more dimension, making this story inside R4. So the Chekhov's original definition is counting immersed disks inside Lagrangian projection, which is not really SFT, but this is in 4 dimension, this counting is actually the J holomorphic curves, so making this rigorous SFT invariant. So once you have that, you can generalize the story into higher dimensions, and that's done by Echolm, N.R. and Sullivan in 2005. So they can do that in the contact R2n plus 1, or more generally, the product of exact symplectic manifold cross R. So the contactization of exact symplectic manifold. In the case of R5, there's a special case of Lagrangian tori, which come from the conormal bundle of knots inside, smooth knots inside R3. It's called the knot contact homology. It was first formulated by Lenny Ying and then proven to be, SFT invariant by Echolm, N.R. and Sullivan. And also there's the computational aspect, like in higher dimensions, having a well-defined algebra is one thing, making that computable is another. So there's a sequence of work of Rutherford and Sullivan for Lagrangian surfaces, and they call that cellular DGA. And also, let me mention that this homology theory here is LCH. You also have a duality on that, which is called Sablov duality. It was first proven by Sablov in 2006 for the Lagrangian knots and generalizing the higher dimensional setting by Echolm, N.R. and Sablov in 2009. So one thing you can, just look at this. It basically says for any augmentation, you have a chain complex, a homology theory associated to that, and there's a categorification for that homology theory. It's first defined by Bourgeois and Shangchuan in 2014, and then there's an alternative version by Ying, Rutherford, Shende, Sweck, and Vassell in 2020. Okay. So that's a DGA story. Let me say a little bit more on another one, the microlocal sheaf theory. So this sheaf theory sort of came into the Lagrangian invariance by this work of Guillaume, Mukashira, and Shapira in 2012. What they did is they, given a Lagrangian lambda, Lagrangian submanifold lambda, they can define this sheaf lambda. It's a DG category of constructible sheaf of perfect compasses. So the definition depends on this important notion of micro-support, which was studied by Kashiwara and Shapira in the late 80s, where they categorify the microlocal analysis, this notion in microlocal analysis. Or maybe I should also, I forgot to include Sato in the reference here. So this important notion basically is the following. If we have a constructible sheaf that's supported, the sheaf is defined on a manifold X, and then you can associate its micro-support in the co-sphere bundle of X, which is a Lagrangian. So using this geometric notion, you can define this category, which consists of all the sheaves which are micro-supported within lambda. So that's the invariant, and this invariant is made very computable by the work of Shende Trumandasso in 2017, where for the Lagrangian knot lambda, we can just take X to be the front projection, and then you can define the sheaf in the front diagram. You got some local pictures that look like this, and locally you can represent these sheaves by representations of quiverous relations. And there you can sort of describe the sheaf explicitly, compute their morphisms, etc., etc. So there's a lot of work, subsequent work after this. Okay, what is the relation between these two invariants we just talked about? In 2020, in Rutherford, Shende, Sivak-Zaso proved the following orientation sheaf correspondence, which says that for Lagrangian knots inside R2, R3, standard R3, there's an A-infinity equivalence of categories between the augmentation category and the category of constructible sheaves, micro-supporting lambda. Some conditions on that. So the reason for this correspondence is not coming out of nowhere. There's a very deep reason behind that. It's proven by Nader-Zaso, another called the microlocalization correspondence, which says that the Fukaya category of the cotangent bundle is equivalent to the category of constructible sheaves. So that's part of main direction to prove the homological mirror symmetry. And I should also mention that the more recent formulation by Ganatra, Pardon, and Shinde, using the partially wrapped category, which sort of generate this to not only the category of perfect complexes, but more generally, on the left-hand side, you can see this some version of the partially wrapped category. On the right-hand side, this is the category of wrap sheaves formulated by Nader, Ko, and other people. Let me move on and talk about, from Lagrangian knots to their Lagrangian fillings, so one-dimensional higher. So our definition starts with the simplexization, where we add one extra dimension to the contact manifold. And the symplectic form is given by, we multiply the contact form with this exponential of t and then take the differential. So this is, by its formulation, is the exact proof form. So suppose we have two Lagrangians, plus and minus, and a cobordism, Lagrangian cobordism is just a surface whose, the two endpoint, the two boundaries are the cylinder of lambda minus and lambda plus, and the being exact here means that this primitive one form restricted pullback to the Lagrangian is exact. So usually, sort of this lambda plus is a more complicated knot, and lambda is a simpler knot. But the notion that we write this cobordism from going from the simpler minus to the more complicated plus is because there's a convention given by the Liouville vector field, sort of a consensus in the symplectic community. And what is the Lagrangian filling? It's when one of the end, the negative end, equals to empty set. So sort of the surface just fills up, it bounds the lambda plus. That's the Lagrangian filling. Okay, so functoriality. I have spent time trying to convince you, or at least survey the history of this invariant, saying that it's SFT invariant. So the cobordism now appears, and then that should be a functor. That's the SFT philosophy. And this is realized by Ekholm, Honda, and Kelman in their 2016 paper, where this cobordism will induce a DGA homomorphism from plus to minus. And sort of the direction sort of goes the other way around. It's contravariant in a sense. And this is a DGA morphism defined by contingent homomorphic curves, as expected. Yeah, I should. This is a literature remark that there's some work by Penn and Rutherford who generalized this functoriality to immersed exact Lagrangian cobordisms. In some sense, like you can look at the Lagrangian lift. It's a Lagrangian cobordism, Lagrangian filling, where they get some roofs of DG algebras, so not just DG morphism. And there's also other complicated structures of the Lagrangian cobordism studied by Shangchuan, Dimitroglou, Rizal, Gigini, and Golovko, and also by Lagou. Anyway, let's focus on this DGA morphism. So we have this cobordism. It induces the DGA morphism. The direction is flipped, and then this will induce a map on the augmentation. So let's recall that the augmentation is a functor of points. It's a map from A to the K. So if we precompose with this phi, the augmentation of the lambda minus will give us a augmentation of lambda plus. So it's this map. And I sort of use the map here, like in some vague sense, like depends on, you want to study, as a set, as a variety, or as a category. So it carries whatever suitable meaning. There's also a data I didn't explain to you, but it's appeared here. It's shading in the gray. There's also some topological data of the Lagrangian filling should be encoded. That's K star to the first Betti number of L. Okay. But anyways, because taking functor of points is contravariant again, now we have a map which has the same direction as L. So it's an important property of this file map, the induced map on the augmentation, is that it is usually injective. And this injectivity has been verified in many contexts. In the very first definition of Ekholm, Honda, Kelman, they did that, and for Lagrangian fillings, and then Penn generalized that to Lagrangian cobordism, and in my work with Shen and Wen, we have like enhanced coefficients. Um, and also on the sheaf category, you sort of have some similar injectivity. This is stronger as it is, categorical and functorial. So Gene Truman has the first result, and also Li and Lianguo. And also, there's this injective map is in some sense also algebraic. That's that's my work with Rutherford. So the takeaway is that this injectivity suggests that just looking at the image of phi, it sort of encodes the data of lambda minus and the Lagrangian covariance L. And in terms of Lagrangian filling, we don't have the augmentation of lambda minus part, and then this torus is everything you have. It sort of tells you that we don't lose much information. The essential part is kept by this map phi L, and that gives us effective invariant to distinguish the Lagrangian covariance L. So, so the story continues. As we said, the image of this map sort of preserves the data of the L, but it's more than that. When L is the Lagrangian filling, we don't have this part, just algebraic torus. And what kind of algebraic structure does the image have? It actually has this structure called cluster algebras. So this is another world which was first introduced by Fomin and Zelevinsky, and also some parallel work by Falk and Gontrov. And the I think I'm and the work of Shen, Truman, William Sassel in 2019, they sort of brought these two topics together. Like, how do we really see the cluster structure inside the contact topology? And they take this picture from their paper. So in these diagrams, these are some front projection of the Lagrangian knot. And between these are Lagrangian isotopes. So basically, it's the same knot. But for this diagram on the left and the diagram on the right, there's a construction in cluster algebra called the zigzag paths. And the symplectic story, you can realize those zigzag paths as some Lagrangian filling. It's called a conjugate Lagrangian filling. And these two diagrams corresponds to two different Lagrangian fillings, and they're just related by these Rider-Master moves. So on the algebraic side, these corresponds to the square move in the cluster algebra, which is some mutation they have, and on the Lagrangian side, it says, okay, these are two Lagrangian fillings which correspond to something interesting in the cluster side. So that's the first example. It's a nice picture here. So let me say a little bit more about their relations. So the cluster structure is basically in some elementary term, it's just a set of cluster seeds. So each cluster seed, the data has three parts. One of them is algebraic chart. And the second data is a quiver, which we usually write Q, where the Q0 is a set of vertices and the Q1 is a set of edges. It's a directed graph. And on the chart, we have a set of cluster variables. The symplectic counterpart for this story is the following. We have a Lagrangian filling, and we can equip a rank 1 local system on the filling. And remember this map that we have been talking about, this injective map. This induces a morphism from this algebraic torus inside the augmentation variety. Okay, and this map, this embedding depends on L. So that corresponds to, so the image here inside the augmentation variety corresponds to the algebraic toric chart in the first data of the cluster variety. And for the second one, we need to choose a system of curves, oriented curves on the Lagrangian filling. And this system of curves will produce a quiver. How does that correspondence work? We just set a quiver whose vertices corresponds to these curves. And depending on the intersection between these curves, we can, each intersection gives us an arrow, edge between the curves, between the vertices. And since everything's oriented, like you can put these intersections with signs, and that's the Q1 part. Okay, and finally, we need a set of cluster variables, which are given by the holonomy of the rank 1 local system along these curves. Okay, so each one of them will be a toric variable, and these holonomy will parameterize this algebraic torus. So these three data, now geometric data, will match the algebraic data precisely. So let me talk about classification. The first classification result was given by Eliashberg and Pavlovich in '96, where they proved that the unknot has a unique exact Lagrangian filling. And then for the TARS2 and knot, the answer we get, it's a lower bound, but it's a Catton number. So that has been first proposed. This Catton number has been observed by this is compounded Kalman in 16, and then proven by Penn in 17 using the DGA, and Schneider, Truman, Williams, Dassel using the sheaf construction. Okay, and then there are some other progress, but it has been suspected that exact Lagrangian fillings are rare. So like this probably should be a finite number. That's what people thought for a while, but that's not the case. So in 2022, Casals and I proved that there exist infinitely many Lagrangian fillings. And the major set of examples we look at are these Tars knots in this table. So the Tars knots are parameterized by this pair of integers. And if you switch the two inputs, it's the same knot. So the number of fillings, the main theorem, the main theorem we prove here are these two red spots. It's 3, 6, and 4, 4. And we prove that they have infinitely many exact Lagrangian fillings. And you can see that every knot on its right and below that is more complicated. There's a cobordism from more complicated to the simpler knot. So once we establish these two have infinitely many exact Lagrangian fillings, all the remaining entries also follows. So from this table, you can find that actually this is like the number of exact Lagrangian fillings is generically infinite. It's only the first row and these three entries are finite. The reason for that is that the underlying cluster structure for these Lagrangian knots, remember there's a quiver associated to that. The quiver associated to these knots are of the finite type. So for the first row, these are type A. Um, the number of clusters is a Cantor number. And the quiver for these three are D4, E6, and E8. In fact, people in cluster algebras, they have already, for a long time ago, they have already able to like exhaust all cluster Cs for all this finite ADE type. And it's the work of M. Bailey. They realized everything, all the clusters, geometric by exact Lagrangian fillings for the finite type and the affine type quivers, and also by Hughes for type D. So that fills in all these entries with numbers. Let me briefly explain the recipe of how this proof is done. So the main geometric recipe is a Lagrangian loop. The Lagrangian loop is an element in the fundamental group of embedding Lagrangian embeddings of a fixed Lagrangian knot inside R3. So this is the space of all Lagrangians isotopic to a given one. So presumably this is an infinite dimensional space, and people were wondering like, what's a like is it contractible or what's the topological property of the space? So this was first proven by Kalman. Finding a non-trivial loop inside here just refutes this to be a contractible space. And what we did, the novelty here is to borrow this concept and use that to construct the Lagrangian fillings. What we did is we graph the loop over time. So that you get a cylinder, which is the exact Lagrangian concordance, meaning that the two ends are the same. But this is in the topologically it's trivial, but in the Lagrangian sense it's not. So we fix a Lagrangian filling that we like, and then you can just add more copies of this concordance to that. And every time you add, this concatenation produces a new Lagrangian filling. And you can repeat this procedure and create more and more Lagrangian fillings. The problem of Kalman's, just using that result is that his loop is periodic. It's n plus n periodic. So after finite step, we are not able to obtain more Lagrangian fillings. So for the TARS 3/6 knot, we need some other Lagrangian loop. So here's an example showing that loop. Let me explain that. So 3 means that there are 3 strands here, and it's this Coxeter element sigma 1, sigma 2 repeating 6 times. But I'm taking a period here, and you can see that this is this pattern 1, 2, 1, 2, 1, 2 within this gray window. And the description of the loop we have is we perform the Reidemeister 3 move along here, just pull that strand downward, and then perform another Reidemeister move to the top. And then we shift the window to the right by 1 generator. After that, what is the resulting element in here? You see this is sigma 1. It's an intersection between the lower 2 strands, and then sigma 2, the intersection between the top 2 strands. So that's 1, 2, 1, 2, 1, 2. Okay. So the word inside this gray window to begin with is exactly the same with the word inside the purple ink afterwards. So that's the Lagrangian loop. And we find that these two Lagrangian loops, they don't commute with each other, and they generate a faithful PSL to Z action on the set of Lagrangian filaments. So if you fix one Lagrangian filament to begin with, and then you iteratively apply these two loops, and then you can get at least this number of Lagrangian filaments, which is exponentially growing infinite group. And for lambda 4, it's a similar construction, and we get the spherical mapping class group of 4 points. Okay, so using these two constructions, we're able to prove that these two Lagrangian filaments have infinite many Lagrangian filaments. Okay, so that's the first sort of first understanding that like we can use cluster. It's a very powerful tool that to use cluster algebra to classify exact Lagrangian filaments, and then there's a very strong connection between the filling and the cluster seeds. So we expect this correspondence, and when the cluster structure is not ADE type, we already find infinite many Lagrangian fillings. But one thing missing in this recipe is that for the infinite type quiver, we know there are infinite many cluster seeds, but the Lagrangian fillings, we find that it's just a subset, which is also infinite. For finite type, you can by construction, that's what the other people did, is that they are able to realize every cluster seed by a Lagrangian filling, and we sort of want to do the same for not only finite type but also infinite type. So this is the second theorem I want to present here. This, what I just said is true. This map is surjective, meaning that the cluster seed, regardless the quiver has type finite or not, everything can be lived to a Lagrangian. Okay, so let me quickly mention the recipe for this proof. So the geometric counterpart for the cluster mutation, which relates different cluster chart, is the Podolowicz survey. So the construction is that given a Lagrangian filling and the Lagrangian disk that it bounds, you're able to perform this surgery and obtain another Lagrangian filling and another Lagrangian disk. Presumably, this disk, the boundary of the disk is a curve on L, which corresponds to the vertices in our quiver. And performing this disk surgery corresponds to mutating at that vertex. But the technical difficulty is that this procedure, this geometric procedure, may not continue. If we want to mutate at a curve which bounds a bygone, and then bad thing will happen. So the solution to that is to use the notion of quiver with potential, which theory developed by Dirksen, Wieman, and Zelewinski, to record how many bygones we have in the configuration. Okay. So what we did is that we can define a geometric quiver with potential, where the quiver is the same thing as we mentioned before. It's given by the intersection of this collection of curves. The collection of the curve is the boundary of the collection of the disk, and the point is that we need this this potential, which is the element in the zeros Hochschild homology of the complete path algebra of the quiver. In explicit term, that's the sum of the polygons bounded by the set of curves. So we have a geometric QP mutation following by this Podorovich surgery. And there's also the algebraic quiver QP mutation, which is defined algebraically. And the point is we need to verify these two are the same. In that sense, this QP will record what happened on the geometric side. One of the key thing to here is to look at what happened after the mutation. Okay, so this is a definition I didn't elaborate too much, but on the algebraic side, the mutation of the potential is given by the sum of two terms. One of them is by contracting the incoming and outgoing arrow. So that will decrease the length of the monomial by 1. Remember, the potential is a sum of cyclic monomials. So this first term will decrease the length of that by 1. And then we have some triangular term. So in this picture, on the left-hand side, this is the curve configuration before the mutation. On the right-hand side, this is the curve configuration after the mutation. And you can see that here, this represents a local property of a polygon bounded by the curve configuration, which pass through these two intersection points, which are two letters in the potential. And after the mutation, this one naturally corresponds to this polygon, which, these two vertices becomes 1. So that decreases the monomial by length 1. So that corresponds to this term. This is a similar construction, which is the same by this one, because the horizontal line is really S1, excluding, at infinity. So this also contributes to this term. And finally, we have this triangular term, this cubic term, which you can see we have a very thin disk. Okay, and the 3 vertices are exactly that. So that's not very thorough interpretation, but I hope I give you a sense that we show the slogan that the algebraic QP mutation corresponds to the geometric QP mutation. And then finally, remember our goal is to prove that every cluster seed is induced from a filling. So we start with a positive Lagrangian, a positive Bray Lagrangian knot. There's a canonical filling which induces a canonical cluster seed and canonical non-degenerate QP. Next, we use a property that for any cluster seed, we can find a finite set of mutations that connects the initial cluster seed to this arbitrary cluster seed. And all we need to do is we just need to realize each of the mutation geometrically by Podorovich surgery. So if the corresponding disk boundary is not part of any bygone, we just proceed and then perform that surgery, that's okay. Otherwise, if it's part of some bygone, then we can remove all the bygones by isotopy, which is looks like Reidemeister 2. And the non-degeneracy of this QP will say that at the end of the day, there's no 2 cycle. So there's no bygone. And then we can continue and proceed with the mutation. And we can iterate this procedure, after finally steps, we're good. So that proves this result and establish the surjectivity of the correspondence. Okay, I'll stop here. Thank you.
Thank you for the talk. Does anyone have any questions?
Mhm. Ah, modeled. You can model those automorphisms. Yeah, I don't know. I don't know. I think even there's one question before that. Is every algebraic automorphism can be induced by geometric Lagrangian loops? I don't know the answer to that either.
Okay. Any more questions?
So when you associate it to every Lagrangian failing cluster variety, you constructed a rank one local system on the L. So is this local system constructed by some explicit method, or is it just an abstract local system so that the cluster variables are free with some relations?
Yeah, it's simpler than you thought. It's the Lagrangian filling is a smooth surface with boundary, and we just look at line bundles on that. So
Yeah, but which line?
all of them. So each one of them gives us a point in the target chart. All of them gives us the entire target chart.
Thank you.
Any more questions? Okay, if there are no more questions, then let's thank Honghao again.